So we had said that the nebular collapse model seems to be very good at explaining the solar system. So it gives rise to these proplyds, which are where the planets are forming in a disk around the star. Now, that's really fine, but it's still not complete yet. Because you start going through the mathematics and you say, well, why do we get exactly the planets that we get? And so now we need to add to this idea a little bit. So the theory would originally seem to suggest that in that proplyd, that things just tended to clump up in several spots, and those clumps, as they clumped up more and more, became the planets. But when you go through the math, it's not that simple. And you realize that the reality is a little bit more complicated. The key is back to that interstellar dust. That interstellar dust has iron and silicates in it, but hydrogen and oxygen are very common out there too. And so hydrogen is the most abundant thing in the universe. And so what happens is this hydrogen will mix with the oxygen and make water. So some of this interstellar dust is actually very icy, almost like snow crystals. And so the nebula is seeded with these dust grains, some of them being rocky dust grains, some being icy dust grains. Now, some of this stuff is still out there. Even when a bunch of this stuff comes together to make planets, a little bit of it never makes it into being a planet. It still continues flying around the solar system for billions of years, where it eventually bumps into one of the planets and drifts down to the surface. On the right here is actually an image here of under a microscope of some interstellar dust, something that was collected in Earth's upper atmosphere by one of NASA's research aircraft. Flies very near, as high as it can, much higher than commercial aircraft, and it collects these dust grains floating down from outer space. And so these things are still out there and gradually adding to the planet. Now, what we believe happens now is that these dust grains out here start to run into each other. And in the early disk, as the solar system is forming, it's actually very hot. And so when these things run into each other with enough energy, they melt. And you get these little molten droplets. And these molten droplets then stick together to make rocks. And the rocks, as they're flying around, can bump into bigger rocks, other rocks, and add to them. And then as time passes, they start running into each other. And then if you got, similar sized ones hitting, they hit each other, blow themselves apart. But if you get big ones and little ones hitting, then the little one embeds itself and just makes the big one bigger. And so what happens is if you sit down and do this mathematically, and they've done this, they've actually had computers that have been running, and they simulate all the orbits of billions of things orbiting the sun, and you turn on this thing and let it run for a while, and you realize that these things start bumping into each other, and they sometimes blow themselves apart, annihilate each other, but sometimes they clump up. They'll sometimes clump up into little small things that, potentially could eventually grow to become a planet. We call that like a protoplanet. And these protoplanets, as more things start running into them, eventually get to be bigger, planetesimals. Okay, I guess you'd call them planetesimals is these things that are growing like a planet, and then they start clumping up into a handful of things we call protoplanets, and then the protoplanets eventually grow and become planets. Now this indicates that the early solar system is very, very violent, with all these smaller things slamming into the big things. In fact, they don't just all happen at once. It turns out that as time passes, you start ending up with less and less of these things running around, but there's still a bunch of them out there. And so for like 1 billion years after the solar system formed, and you get planets, those planets are being bombarded by asteroids, and small planets even. I mean, even small planets can hit the bigger planets. And so that can all happen in the first billion years of the solar system. And so this turns out to be a very violent process. Some of these things might actually come in and gravity slings them into the sun, or they might miss a planet and gravity slings it out of the solar system. And so this kind of process is what we believe really happened. Again, computer simulations going through all this show if you put a whole bunch of these things out here flying around, then eventually, after enough time, they will end up being just a handful of objects orbiting around in roughly the same direction. Well, in exactly the same direction, in roughly symmetric orbits. And so that's what we see in the solar system. Okay. This idea is basically what we call planetary accretion. The dust grains gradually, grow larger as they run into each other and merge. They form as shock waves pass through the planetoid. As the young star, the sun starts, settling down, disturbances and just random processes, turbulence in the planetoid sends shock waves through it that compress things and make little droplets that we call chondrules. These are little liquid droplets that can stick together. The chondrules will actually stick together and make a rock that we call chondrite. So those chondrites, become the first meteorites, the first big solid things in the solar system. As chondrites run into each other, they eventually merge and form like miniature planets that we can call planetesimals. These are almost like asteroids here out there. And so these planetesimals are forming, and they eventually will collide and form into protoplanets. Or they might not. There's actually some indications that maybe some of those leftover planetesimals became the asteroids and the comets. If it's an icy planetesimal, it becomes a comet. If it's a rocky planetesimal, it becomes an asteroid. Eventually, these protoplanets, once they get big enough, they eventually become the planets. Because things keep running into them. Once they get big enough, then it's unlikely that anything is going to be big enough to run into them to blow them apart. Even Earth, if it got hit by something the size of Mars, which is much smaller, would survive the impact. It would devastate the planet. I mean, the planet would be pretty much liquefied by the impact, big blobs of stuff coming out. But when everything settled down, there would still be an Earth here. It would not be recognizable as today's Earth, but it'd still be an Earth. It would still be a planet. So once they get to that size, then you would generally call them a planet rather than a protoplanet. And so, and again, there's no real strict definition that delineates a planet from a protoplanet or a planetesimal or even a very large asteroid or chondritic asteroid. There's not really a defining size between the two. They just kind of all gradually merge together. We do see evidence of this having happened. There are chondritic meteorites. And so inside these meteorites, we actually see these little nodules that are left over from the formation of the solar system. We actually have a couple chondritic meteorites on campus, and so when we get to this part of the semester, I like to let people hold this meteorite and point out that when you're holding this meteorite, you're actually holding a rock that's older than the planet you're standing on. Now, the chondrites, the interstellar dust, planetesimals, and so forth that form from that form at different distances from the young sun in the solar system. And so as they do that, the ones that are close to the sun are going to end up being hot because the young sun is going to be heating up. So that means that ice is not stable. Ice will be stable far away. And so if you're several AU out, you can have ice as part of your chondrites, and so you have icy asteroids. Well, since hydrogen is the most abundant thing in the universe and oxygen is pretty abundant, then that means you would have a whole lot more things to build planets with. That means you could build bigger planets. Once you get planets that are big enough, they're going to have enough gravity to hold on to hydrogen and helium. Remember, Earth doesn't have much hydrogen and helium because we don't have enough gravity. But Jupiter, Saturn, Uranus, and Neptune are bigger, and they have a lot more gravity. They can hold on to the hydrogen and helium, which makes up most of the universe. So that means that the bulk of those worlds, once they get big enough, they can hold on to enough hydrogen and helium to actually make up like half the planet. Okay. And so you get really far out, and then you even have methane as part of the stuff that can be part of the solid things. Methane, ammonia, and then you can build even more protoplanets and things out really far from the sun. And so we call this like the ice line, or the frost line in the solar system, the distance at which from the sun that inside that water is not stable as part of the building blocks of it, and outside it is. And so that's why the inner planets are going to be mostly rocky planets, and the outer planets are going to be made of icy things on the inside, but once they get big enough, they can hold on to more gas, and that can allow the planet to get vastly bigger. So that explains the gas giants in the outer solar system and explains the rocky planets in the inner solar system. Pluto is actually a combination of all these icy things. So Pluto, rather than being a full-on planet, is really more like a planetesimal, like a leftover from the formation of the solar system. Now, when it was demoted from the list of planets, a lot of people were upset about that. And I actually thought that made Pluto really much more interesting to study, because it makes Pluto not so much just another planet, but Pluto is like a remnant of the very beginning of the solar system. Pluto is one of those planetesimals. It's one of those things that never made it into a planet because something happened and shut off the process of planet formation and left that as a remnant of that earlier age. So that makes Pluto really a fascinating object to study. So don't feel sorry for it got kicked off the list of planets. It got kicked into a list of even more interesting things to study.